In this video, we will be covering the history and development of the atomic theory from Democritus to the modern era. We begin with the early Greeks. The first gentleman we are going to introduce you to is Democritus. Democritus lived in the time of 460 to 370 BC, which is about 2,400 years ago. He said that all things were made up of tiny, indivisible particles called atomos. There were different types of atomos that existed, and that they combined in different ways to make everything around us. Although he really had no evidence to support this, it was widely accepted. That is, until Aristotle came along. Aristotle lived from about 384 to 322 BC. He said that these atoms that Democritus had talked about were indeed indefinitely divisible. You could keep taking sections and splitting them in half forever, and thus could not be what everything is made of. He thought that there were really only four main elements that made up everything around us, and those were earth, fire, water, and air. Again, without having any evidence to support this theory, it was largely accepted for the next 1,000 years, when we had more advancements in testing and more could be done to look into this. With these advancements, three laws relating to matter and atoms emerged. The first one is the law of conservation of mass. This was developed by Antoine Lavoisier. The law of conservation of mass states, mass is neither created nor destroyed in ordinary chemical reactions and physical changes. Basically, whatever the reaction starts with in mass, you are going to have when the reaction ends. Maybe in a different form, it may be different elements put together in different ways so that it looks completely different. But in this chemical reaction, everything mass-wise has stayed the same. We have not lost or gained any mass. The next law is the law of definite proportions. This was developed by Joseph Proust. In his law, he states, a chemical compound contains the same elements in exactly the same proportions by mass, regardless of amount or sample. So if we were looking at the mass of carbon to the mass of oxygen, it is always going to be the same ratio of carbon to oxygen, or 12 to 16. It's always going to be the same ratio no matter what the sample size that we are looking at. So if we are looking at a small sample that is just carbon and oxygen, or if we're looking at a larger sample that contains many carbons and many oxygens, if we look at their mass ratio of carbon to oxygen, it will always be the same. The third law is the law of multiple proportions. This was developed by John Dalton. The law of multiple proportions states, if two or more different compounds are composed of the same two elements, the ratio of masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. So again, we are looking at a mass ratio of one element to another. So if we looked at a ratio of carbon to oxygen, it is always a 1-to-1 ratio. If we looked at carbon dioxide, in which we have one carbon to two oxygens, it's always a 1-to-2 ratio. So you can't have half of a mass. That these elements always have to combine in whole number ratios so that their masses have to be whole masses. You can't take half a mass of the element. This leads us to Dalton's atomic theory. As we read through Dalton's atomic theory, you're going to find it very similar to the ideas that Democritus thought of about 2,400 years ago. Dalton's first postulate states, all matter is composed of extremely small particles called atoms. Very similar to what Democritus said. Democritus said things are made up of extremely small particles called atomos. So just kind of reiterating what Democritus had developed or come up with. Dalton's second postulate says, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements will differ in size, mass, and other properties. This also goes along with what Democritus has said so many years ago. Basically, if we look at the dark blue circles, these could be some kind of atom, a blue atom if you'd like. They are all similar in size. They are all similar in mass, 5 grams, and then other properties. They're all blue. So basically, if they look alike and all their properties are similar, they must be alike. However, if they start looking different, their properties are different, their size is different. For example, if we move over to the next box where we have these light blue circles, you can see that these, although are all similar to each other, they would all be the same atom, but they're going to be different from the dark blue circles. So if you change what it looks like, how it acts, you've changed the type of element it is. Dalton's third postulate says, atoms cannot be subdivided, created, or destroyed. This is taking into account that law of conservation of mass. So if you can't subdivide them, you can't create them, you can't destroy them, that means you're always going to have the same amount that you started with and end with. So these two ideas, created or destroyed, are going to be the law of conservation of mass. If they can't be subdivided, kind of goes along with the idea of that you can't have partial, so no partials. Can't have a partial atom. Dalton's fourth postulate says atoms of different elements combine in simple whole number ratios to form chemical compounds. So again, we have to always put together in whole number ratios. So that should sound very familiar to the law of multiple proportions. So this law, of course, developed by Dalton, probably as he went through this atomic theory. So if we're going to put things together, you can see at the bottom we have 1 yellow to 4 red to 2 blue. We can't have half of a blue react. If you're going to combine, you take the whole atom, you can't take part of the atom. So like in the second one, we have 1 red to 2 blue. Again, you can have whole atoms, we cannot take half atoms when they combine to form these different elements. Dalton's fifth postulate states that in chemical reactions, atoms, as seen with the red and the blue circle here, can be combined. You can take an atom that is combined and it can be separated, or we can take two different compounds and we can rearrange them. In all instances, what we have started with is the same as what we've ended with. It just may be in a different form. So this definitely goes along with the law of conservation of mass. Because our two separate elements combined, our combined element separated, or what we had to begin with, traded partners, so that we haven't lost any circles, we haven't gained any circles from how our reactions started. So this leads us to the modern atomic theory. Modern atomic theory has changed just a little bit, and that's due to advancements in technology. So the first advancement, our atoms are divisible into even smaller particles. So we know today that the atom isn't a solid atom, as Dalton thought and Democritus thought years ago, but it is divisible, which kind of takes into account what Aristotle thought, that we can keep breaking these things down. But the atom that we look at today, although we say that we see that it is divisible, the atom itself and all of its parts are what are unique. So the atoms we know are divisible, and those are into, maybe you've heard of quarks or leptons, and the list goes on and on. They've found more and more with the smaller that we can get and the better types of microscopes that we can look at. We also see that one element can have atoms with different masses, and these are called isotopes. And we get into isotopes in a later video in this series. So what this is basically looking at is that idea of if an atom looks alike, has the same properties, it's going to be the same, but if it has different properties, it's going to be different. Well, we're going to find that if we change masses, we're still the same element. So that whole idea of a different mass being a different element doesn't hold up anymore. The atom is defined as the smallest particle of an element that retains the chemical properties of that element. If we break down the atom into its smaller subatomic particles, we find that we have the same properties across all kinds of atoms. So no matter what atom we're looking at, the property would be exactly the same. So the atom, with all of its subatomic particles, is the smallest one that retains the chemical properties. We need those specific amount of subatomic particles within the atom to give each element its identity. So the subatomic particles contained in an atom are the electron, which are the green things on your screen moving around, and these carry a negative charge. Within the nucleus, which is the red area of the atom, we find the proton. The proton has a positive charge. Also within the nucleus, we find the neutron, which is neutral in charge. So the composition of the nucleus, found with further testing, we say that it's made up of a positive, which is the protons. Well, the protons have a mass of 1.673 times 10 to the negative 27 kilograms. Again, we see that this is small, but compared to a negative 31, it's actually quite a bit larger. So this actually does have measurable mass. And for our sakes, we're going to give it 1 AMU, atomic mass unit. So like later we said grams, we'll get into why we say gram, but we really want to call it an atomic mass unit, as we haven't really realized why we're going to call it grams or 0 grams. I guess since it's 0, we can give it any unit. 0 means nothing. In this case, we're going to give it 1 atomic mass unit, so 1 AMU. So again, I'm not going to have you memorize that number. Just know that it is quite a bit larger than the electron, so we're going to give it 1 AMU. Because we have neutral atoms, we're going to say our number of protons must equal those number of electrons that are in there. We can't see them, but we know they must cancel each other out. And it's this number that's going to determine the atom's identity. So we find that if we change it, our mass changes, our identity changes. That goes along with that second postulate, of Dalton's theory. Then we have the neutrons. If we just had protons, we would find that we still do not have the total mass that we need for the atom. It's only about half of the mass. So there has to be something else in there, and that we called the neutrons. These are going to be those other particles. They are neutral in charge because they're not going to affect that positive-negative balance that we already have, but they are going to give us the rest of our mass. As you can see, it's got the same negative 27, and the numbers only differ by this 3 and 5. So relatively the same mass. So again, if we give the neutron a mass, we're going to call it 1 atomic mass unit. So virtually they have the same mass. But we do find that the neutrons can vary from atom to atom of the same element. So we can change this mass a little bit, but not really change the properties of what that element is. If we change the proton, it does change, but the neutrons we're going to find can change and not change the element. And finally, we're going to look at nuclear forces. We know that the nucleus is such a small space. If it's such a small space, how can we have 2 different particles inside of there, let alone have a bunch of positives that are in a very small compact space? By law, by this whole idea that like charges repel, they should just fall apart. They should be exploding from each other. There's no way they should be in such a tight packed space. Well, they are held there by these nuclear forces. These are forces of attraction that happen between a proton and a proton and a neutron, and neutrons and neutrons. So they're stuck together. And they're caused by this extreme closeness to each other. And this is a very, very strong force. This is what we use for, let's say, nuclear bombs. If we are going to finally break apart that nucleus, that force is going to be so strong, used to break it apart, that the energy that is released gives us the nuclear bomb.